Okay, so welcome back. We've got two more talks, and then there is a slightly more advanced workshop that Johan is going to lead us in. So again, usual format, we'll have two talks of 28 minutes or so each, and then we'll have a bit of time for discussion and questions. My pleasure to introduce for the first of those, Jeremy Avigad on teaching with Lean. Thank you, Jeremy.
Thank you very much. So I'm sorry I can't be with you in person, but it's a pleasure to be with you virtually. And like Heather and Patrick, I'm going to talk about some of my experiences teaching with Lean. But the first thing I want to do is start with just a little demonstration of Lean. So it's hard to talk about Lean, unless you've actually seen it in action. So just in case it is new to some of you, I'd like to show you what it looks like. And you can actually run a similar version of this demo in your browser. If you go to my webpage and look under talks, you'll find a link. It's with a talk associated with the acronym CBMS. But anyhow, so here it is. So let's see. So hopefully now, also, if you have any trouble hearing me, let me know, speak up. Again, it's hard not being in the room. But if things are going well, you should be looking at Lean running in VS Code. And so on the left is the document that we're going to work on, and on the right is the famous Lean info view window where Lean gives you its feedback. And what you're looking at on the top here on line 7 is definition of the Fibonacci function. So we're starting with 0. So the fib of 0 is 0, fib of 1 is 1. And then for every natural number n, fib of n plus 2 is fib of n plus 1 plus fib n. A nice thing about Lean is that it's computational, so you can you can evaluate Fibonacci numbers and and see them. You can run them right away. This, by the way, is a horribly inefficient implementation of the Fibonacci function. Another thing you can do in Lean is define a more efficient, computationally efficient version and prove it's equal to that one. Let's also, so what I'm doing here now is I've made a list of the numbers from 0 to 19, so the natural numbers less than 20. And now what I'm going to say is just apply, the Fibonacci numbers to each of them. There we go. And you see that, computes the initial Fibonacci numbers. And what I want to do is work through a proof of the formula for the Fibonacci numbers in terms of the golden mean. So on lines 14 and 15, I've defined, the two roots of the equation x squared equals x plus 1, so the golden mean and its conjugate. And so the first thing we want to do is prove that they meet that description. So pi squared equals pi plus 1. And so let's start by just, kind of simplifying and unfolding. And you see Lean kind of unfolds the definition and then didn't do too much more. But if you notice there are fractions around, you might know that, in fact, there's a tactic in Lean called field sim, which does a little bit better. Actually didn't, again, it cleared the fractions, but it didn't do too much more. What we really wanted to do is expand the product, the 1 plus the square root of 5, we wanted to multiply through. And there's a tactic that is good for that called ring, which didn't work, but Lean suggested doing ring NF. Again, we're still not done. It kind of did, it calculated, it kind of simplified some more, but then you see that it didn't really simplify this square root of 5 squared, which is kind of annoying, but we can tell Lean to do that by saying simplify. And now we're back to just a ring calculation. We just wanted to kind of evaluate and collect the square root of 5. And so now ring will finish it off. Oh, by the way, I'm not doing this demo as kind of a lesson plan or something I recommend doing with students. I just want to sort of give you a feel for what it is what it's like to work with Lean. Okay, so we've just proved this calculation. And so this is one piece of information. I mean, Lean is not all that great at just kind of hacking through straightforward calculations, but you can get it to do that with enough coaxing. And the nice thing is virtually the same proof works for the conjugate. I just have to change phi to phi prime. Okay. And so, if you multiply it through by phi to the n, what you get, the equation here, the first one is phi to the n plus 2 equals, phi to the n plus 1 plus phi to the n. which really looks a lot like the recurrence. Well, it's just like the recurrence for the Fibonacci numbers, and the same for phi prime. And so, if you do a little calculating, you can, convince yourself that the right linear combination of the two is this one. So 1 over the square root of 5 times phi to the n minus phi prime to the n. But, if you're not sure, if you really want confirmation that it's correct, let's have Lean prove it for us. And the proof should go by induction. And the induction is, we're going to actually mirror the induction on the definition of Fibonacci numbers. So in other words, we're going to do the 0 case, the 1 case. And the error message here is, Lean is telling us that I haven't done all the cases. But here, let's do the n plus 2 case. Okay, let's see. So the 0 case, if I just tell it to simplify and, unfold the definition of Fibonacci numbers, Lean can get that automatically. We can try the same thing here. Simp fib. Oh, but then we get the definitions of phi and phi prime. And then, it's again now a calculation. So we may remember, okay, field simp does a little bit better. And so that got it. So now here's the more interesting case. Let's prove this. So in this case, if we look, so if we look at the goal, we're trying to show that fib of n plus 2 is equal to, is equal to that. But we should be able to use the inductive hypotheses. Okay, so first, let's simplify by unfolding the definition of the Fibonacci function. So that helps a little bit. In fact, let's do field simp to get it to clear denominators. Okay, but so now what we want, so we have phi and phi prime on the right. We want to use the inductive hypotheses, for n plus 1 and n. And it turns out we can tell Lean to do that by just actually telling it to use the theorem that we're in the middle of proving, the equation that we're in the middle of proving. And Lean is smart enough to know that it's actually applying it to structurally smaller values, so smaller natural numbers. And now we're moving along. So we may notice that we have phi to the n plus 2. And so if we expand that to phi to the n, times phi squared, then we can use our lemmas for phi squared and similarly for phi prime squared. So the lemma we need is POW-add. And it talked, Heather talked about the annoyance of having to know names of lemmas and theorems by heart. So here's just an example. I just know that the identity that says a to the b plus c is a to the b times a to the c. It's called POW-add. And we're making progress. You see, here's a phi squared, here's a phi prime squared. So let's give the lemmas phi square and phi prime square. And and now it looks just kind of like a mess, but it looks like if you kind of multiply through and cancel, maybe it'll all work out. And there's a tactic for that, and we proved it. Okay, so that's the proof of one elementary identity in Lean. And for another example, let's prove that there is a root in the real numbers, the equation x cubed plus 2x plus 1 equal to 0. And so, okay, so we tell students, one way to prove this is to actually find an explicit root, but that's going to be hard in this case. But this is, to any calculus instructor in the room, this is something that you tell your students that they can do with the intermediate value theorem, right? So if we find a value where the expression is negative, so for example, -1 should work. And we find another one where it's positive. So let's see, if you put in 0, it's positive. Then between -1 and 0, we should get a root. So let's try to prove that. So first of all, let me give the expression a name. Let f of x in the reals be x cubed plus 2 times x plus 1. Okay. And okay, so we want to use the intermediate value theorem. So the first thing we have to do is find the intermediate value theorem, find the name. So let's go before the theorem and start typing. So we start typing intermediate. Let's see. Okay, so tab completion helps. But now we get this kind of embarrassment of riches. There are all these variations on the intermediate value theorem, which is a little bit overwhelming. The ICC one, you need to know that there are lean conventions. This stands for the closed interval. So I is for interval, C is closed both endpoints. And if you look on the right here, you see, well, there's a documentation. It says this is the intermediate value theorem for continuous functions. And the theorem, let's see if I can get, let's see. Try to see if I can make it bigger, Control Tab. Okay, bear with me. Let's see. Trying to figure out how I can make there we go. That's still not helping. Can I make that bigger? That didn't work. Try making it bigger that way. Interesting. Okay, I usually do this with a bigger monitor. But here you have a statement of the theorem. And again, like a lot of things in the math library, it's might not be immediately recognizable as what you want. But the theorem says that, well, again, it works in great generality, but it says if A is less than or equal to B, and F is continuous on the closed interval from A to B, then the closed interval from F of A to F of B is contained in, it's kind of off the screen, but hovering. Let's see, maybe hovering brings it up. Let's try that. There we go. Okay. Then the closed interval from F of A to F of B is contained in the image of the closed interval from A to B. Okay. So it should be sufficient to show that 0 is in the closed interval from -1 to 0. Okay, because this says this will say that there is an x between -1 and 0, such that f of x is equal to 0, and then we should be able to, close interval, and then we should be able to use that. Then we should be able to use the intermediate value theorem to prove that statement. Right. So, So to prove that the sufficient statement suffices, So I'm doing a lean trick where we're going to start by telling lean that the theorem is done, even though it's not. And then when it complains, we're going to fill in the information. So what I'm going to do is I'm going to simplify and unfold the meaning of this statement. I'm going to ask the simplifier to unfold what it means to be for 0 to be in the image of the closed interval under F. I'm going to say sim at this. And now you see that it says exactly what we think it should say, that there is an x between -1 and 0, such that f of x is equal to 0. The goal just wants to show that there is an x, such that f of x is equal to 0, without that side condition. But fortunately, Lean's built-in automation can do that. And now to prove the statement, we want to apply the intermediate value theorem. And now Lean shows us that there are 3 things we need to prove. So first of all, we need to show that -1 is less than or equal to 0, which we can do automatically. The second thing we have to prove is that f is continuous on that interval, but f is a polynomial, and Lean has automation that can figure out that a polynomial is continuous. So it's called fun prop. And finally, we need to show that 0 is in that interval. And so let's simp and unfold f. And then it's just a numeric calculation. So we can do that with norm. Okay, and so that was a quick 15-minute demo of Lean. Okay. So as far as teaching with proof assistance, this kind of interaction has a lot of benefits. So students, get immediate feedback and encouragement. They get error messages, whenever they do anything wrong. You see, as you're working through a proof, you have information about where you are in the proof, what you need to do, what objects you have at your disposal, what hypotheses. And it gives you a way to, you can try different things. You can, finish a proof, you can edit it, you can rewrite it, you can explore. And all of these things, I think, taken together, give you increased student engagement that, when you're sort of working through the material, you're on, right? You're interacting with the computer, you're frustrated. When things work out, you're happy about it. And I think that keeps students engaged. It's also nice that, if you use proof assistants for teaching, it's nice that proof assistants are generally useful outside of teaching in academia and industry. And so, you're giving students skills potentially that may be useful later on. But, you've also seen some of the downsides in the quick demo. There's a very steep learning curve to using a proof assistant. The syntax is very fiddly and unforgiving. The error messages can be confusing. And again, as Heather emphasized, you really need to know the names of your theorems, the functions, the tactics, the commands that you can type. And so one general concern is that, that this can really distract from teaching the material that you want to teach, from teaching the mathematics. So, before you started by using Lean, you had one body of material to teach, and then you decide to use Lean, and then you have two. Which may not help. And another concern, I think, is that, when students interact with the computer, it almost encourages just kind of hacking away and clicking and, not really thinking. And sometimes you want students to, to shut down their laptops and just go for a walk and think about things. And so there is concern that, the technology may discourage them from doing that. And, we've all developed coping strategies as far as dealing with the complexities of proof assistance. When we teach, we don't ask students, you pick and choose your tasks very carefully. You give them very specific things to do. And then you try to make sure that they have all the information that they will need to succeed. So you give them lots of examples, you give them, hints and the background knowledge, you make that, salient right before you give them a problem. You can also hide some of the complexity by giving them nicer interfaces. And then over lunch, Megan and Harvey gave a great presentation on the use of AI. I think that's also a new frontier about how AI might help with the learning. But as far as the broader concern as to distracting from the material and preventing students from thinking, I think it's a good idea to think of a proof assistant as a supplement for your other, teaching assessments and teaching methods, rather than something to replace them. So it's best used, I think, in conjunction with more traditional methods. So over the years, I've taught a number of courses based on Lean. I've taught a course on interactive theorem proving. I'll be teaching that again next semester. And for that, I use a book that I am co-authoring with Mathematics and Lean with help from lots of people in the community. I also teach a course to third-year computer science students at Carnegie Mellon called Logic and Mechanized Reasoning. That's based on another online textbook that I've written with Marijn Hoyle and Wojciech Nawrocki. But today I'm actually going to talk about a course that called Logic and Proof. So it's based on a book that I wrote a number of years ago with Rob Lewis and Floris Van Doorn. I haven't taught it in a few years now, but colleagues have picked it up. So it has been taught at Carnegie Mellon with the same materials. And I think that's most appropriate for this workshop. So the course was designed for first or second year students, university students from a variety of background. So they weren't assumed to be math or computer science majors. In fact, we had business majors and language majors and so on. And the course was designed to be an introduction to symbolic logic, informal proof, and formal proof. And the textbook is written for Lean 3. The course materials are prepared for Lean 3. But Joseph Waugh just taught it this past summer. And so I believe he has the materials reasonably well ported to Lean 4. And the goals of the course were to teach, primarily I'd say to teach students to write mathematical proofs, informal mathematical proofs. But along the way, we also give them an introduction to symbolic logic. And there, the idea is that symbolic logic is interesting in its own right, but the hope was that a background in logic would give them insight to the way ordinary mathematical proofs work. And we also teach students Lean in service of those other goals. And so you can still find the textbook online and the course materials online. And the topics were, in logic, we teach, propositional logic, natural deduction, first order logic, truth assignments and models, an informal notion of what it means for a formula to be true in an interpretation. The mathematical topics is sets, relations, function, proof by induction, a little bit of elementary number theory, and so on. And then the lean exercises supplement pen and paper proofs, are both supposed to address both. So we have exercises in logic, propositional and first order logic, but then, elementary set theoretic identities and, properties of functions, and so on. And the idea is the material in each strand was supposed to be just run-of-the-mill, entirely standard. So if you're teaching an introductory logic course, we wanted to make it as plain, vanilla, straightforward a logic course as you would expect. Similarly for sets, relations, function, and so on, we wanted to be absolutely standard. The novelty being that that we were doing, the three of these things in parallel, in the hopes that they would kind of reinforce each other. So, for example, here is a homework problem that we gave to students. So let f be any function from x to y, let g be any function from y to z. Show that if g composed with f is injective, then f is injective. And then there was a second part of the problem that shows that that G might not necessarily be injective. And here is actually an answer. This is kind of, I transcribed an answer from a student's homework. And it's a pretty good answer, not perfect, but the homework goes, assume that G composed with F is injective. Then by definition, for all A, B, and X, we have that G composed with F of A equals G composed with F of B implies A equals B. Then the student says, now assume that there exists some x, y, and x such that f of x is equal to y. Then, the composition of x applied to x is equal to f of y, which implies x equals y by the injectivity. And so one negative thing is that the student here uses the double arrow. I don't think they got it from us. I don't think we use it on the blackboard, but we tell them, in proofs, don't use, use language for the logical connectives. Don't use the arrow. And then sort of a more annoying error is that, the now assume that there exists some x, y, and x. I mean, we really want them to say, let x and y be arbitrary elements of x. But, the student has learned how to say there exists or associates that with mathematics and so finds elocution in terms of that. So these are things that the grader, would comment on the homework and try to beat it out of the student to, use the right notation and the right locutions. But at the same time, here is an example of the proof in lean, and I think we would give them this one on the next homework assignment. But if they've done the pen and paper proof, it's not too hard for them to do this. So this is something. This is actually, I think, taken from. No, I'm sorry. I've translated it to Lean 4, but this is similar to what we would expect students to write. So, for the first problem, the reading is let x1 and x2 be elements of A. Suppose f of x1 is equal to f of x2. Then g of f of x1 is equal to g of f of x2, just by substituting that identity. Then you need to show that x1 is equal to x2. Well, that's just injectivity, applied to f of x1 equals f of x2. Right? And so by the end of the course, students can do exercises like this in Lean. And so, some observations about the course. So, from the beginning, we make it clear to students that they're using 3 distinct languages, that, they're doing ordinary mathematics, they're doing symbolic logic, and they're doing Lean. They're doing a formal proof language. And, before the course, we agonize about how to not get them confused or how to smooth out the differences. That was not a problem. Students are happy to, learn different languages and they can recognize the correspondences, the relationships. You can talk about how they're the same, how they're different. But, they can switch contexts. They seem to be able to switch contexts pretty well. And moreover, doing all 3 at once do seem to help them in the sense that when giving in ordinary mathematical proof, if we point to the blackboard and say, what's going on there, students can say, oh, that's just exists elimination, or that's just proof by cases. So they were able to relate, in the informal proof, the things that we were doing formally. And finally, every time I taught the course, students seemed to like it. And we would query them, which part? Do you like the math part? Do you like the logic part? Do you like the Lean part? And, the answers were kind of varied in a healthy way. There was no clear favorite, and for the most part, they seemed quite happy with the course. Okay, and so I just wanted to mention a few other efforts that I know of along these lines. So you've already heard about Heather's course, which I'm a big fan of. So mechanics of proof, and I really like the fact that she has students do both pen and paper proofs and lean proofs of the same problems. And she has reported that these students, some students do the pen and paper proof first, and then try to formalize it. Some of them do it the other way around. So that to me is good evidence that the skills are reinforcing each other. You've also heard Patrick's very nice presentation about verbose lean, which again I'm a very big fan of. There are a couple more that I think are worth mentioning. So Daniel Velleman is an author of a popular introduction to proof called How to Prove It. He actually has written a companion called How to Prove It with Lean. And let me see if I can open it here. So, it's here. And let's see about Lean. Wait, about this book. I'm looking for the table of contents. See if I make it bigger. There it is. So it's proofs, relations, function, induction, number theory, various proofs by induction, recursion, number theory. You get Euler's theorem, and at the end, infinite sets. You get through the Cantor-Schroeder-Bernstein theorem. So Dan is retired, so I think he hasn't used this. I don't know anybody who's used this. I'm curious to know. It looks good to me. I expect it should go over well with students. So I'd be curious to hear, if anybody's tried it, how it works. And then finally, also I'll mention in passing. So Heather also mentioned Sina Hazratpour. Has in part built on her material, but has also written material of his own. So he's has a course based on Introduction to Proof that uses Lean as well. And he's used this successfully with students at Johns Hopkins for a few years now. Okay. All right, so let me, so these are all, approaches to teaching mathematics with Lean that I'm a fan of. I still don't feel like we have the ideal solution. So, if you think about teaching with Lean, I think this is a great time. We're on the frontier. We're all figuring out how to do it. If I were to do it again, logic and proof. So logic and proof was designed to be an introduction to logic and an introduction to mathematical proof at the same time. I think if I were to do it again, I would focus on just teaching mathematical proof and then tone down the logic a little bit more. So you don't need that much logic to make sense of the mathematics. And the course very much feels like doing, two things at once. Patrick and Heather, will tell you, as will I, that, whenever you use Lean for teaching, you end up, really picking and choosing your material carefully and tailoring your approaches, to what works well with Lean, which is a little bit of a downside. I mean, you really want to sort of design your course independently of Lean and then just kind of slot it in. And so, we're still kind of struggling to use Lean to teach mathematics the way we would do it, without Lean. But let's see. So before, I used to think that controlled natural language was a bad idea. Patrick has largely convinced me otherwise. But still, my inclination would be not to shy away from the formalization. So more like Heather's course, to teach both the informal and the formal in parallel. So I think you want students to learn both. And so I would try to synthesize them. And then I am also hopeful that going forward, we can, in Lean, over the years, we'll have better automation that will really, so whenever there's a step that students would take that's really obvious, that, you can just say, this is obvious, and Lean will accept it. Okay, so let me just finish with three final thoughts. So one final thought is that one thing that's great about Lean is that the social media group, the Zulip group, are a tremendous resource. People help each other learn how to use Lean. So newcomers, come ask questions, people help them, and they stick around and help the next wave of people learn to Lean. And I think that's a really powerful thing. And so if we can figure out how to expand this mathematics more broadly so that, students can teach each other mathematics, then we'll have a powerful way of extending access to mathematics to a much broader community. We need a lot more educational research. Patrick, Heather, and I will tell you that we think it works well. Students seem to like it. It doesn't seem to hurt. But we really rely on Atina and others to really come up with the educational data to confirm our intuitions that we're helping students rather than hurting them. And then finally, I just want to raise one caveat. So as I said, I think technology has this powerful potential to increase access to mathematics. Just the way that kids today can go online and kind of learn how to program and find online tutorials and experiment on their own. But even for that, we know full well data shows that the kids who benefit from kind of online programming tutorials and educational software are the ones with parents and teachers and financial resources that can support it. In the US, the digital divide, it's usually meant to talk about people, the concern about having access to, laptops and the internet and so on. But I think an even bigger problem is having access to the culture and the know-how, having teachers, having mentors, that can show students how to use the technology and encourage them and get them over the hump so that they're sort of empowered to explore on their own. And so I think there's a danger that if we're not careful, that the situation will only get worse. I mean, and rather than increase access, we'll have even sharper divides. And so that's something that we should keep in mind and try to address. So thank you very much.
Thank you very much, Joan. An excellent warning there at the end. As usual, we're going to go straight on and save the questions and discussion for later. So Achim is just going to come up and share your screen.
Essentially.
Lovely. So my pleasure. Now for something slightly different, right? We'll be talking about lean.
More or less. On the one side, yes. On the other hand, a lot of what I want to say has already been said. So we will see the similarities and the differences.
Excellent. So we have Achim Brucker, Diego Marmsoler, who's online. Achim's here in the room and going to be talking on introducing Isabelle to students with little maths or theoretical computer science background.
Yeah, that's essentially now the opposite from the student cohorts that you are working with. Clearly, why are we, so Diego and myself, we are computer scientists, so maybe at least I much more prefer the German term Informatica, which is that kind of combination of information sciences or working with information data and mathematics. Why are we looking into theory improvers? Because we build a lot of systems where testing is just not good enough. And one of the earlier examples is the Pentium floating point division fault, for those people that can still remember that. That was around 1995, where the division algorithm implementation of the very first Pentium processors was implemented wrongly and ended up with wrong results for certain inputs. And this was one of the famous equations here, where obviously we immediately see that division should cancel out. Then we subtract the same numbers, that should give 0, but it was 256 on Pentium processors, and that was pretty costly for Intel because they essentially then had to offer everybody a replacement. And for me, that is also one of the things that brought me into that field. Essentially, my final year project was around doing formal verification of division circuit algorithms for exactly spotting those mistakes before they make it to the silicon. In the UK, we have a long ongoing issue with software not being correct and people being imprisoned. The post office scandal, essentially a financial system that did the calculations wrong, and the post office was blaming the individual owners of running the local post office branches that they were taking money out of the pocket of the post office, but indeed the software was wrong. And I'm not living long enough in the UK to remember how long that actually is ongoing, but I think over 20 years. It's being now currently rolled up, and we now learn all the details because the court cases are currently going on. And then I'm working in security. People that read the security news might have seen this picture, and there we can immediately discuss if that jeep that is here off-road Obviously not intentional if that is a safety or security issue. If we read the headline that hackers were responsible for that situation, then we suddenly call it security. But again, it's a bug, a problem in a software or hardware system that shouldn't occur, and those systems just have to be correct. As we know, proofs are one means of convincing us really that things have the properties that they should have. So teaching methods for ensuring the correctness as well as safety and security should be an integral part of any computer science curriculum, in my opinion at least. I'm pretty sure Diego will agree here as well. And formal verification, for example, using interactive theorem proving, is such a method, so there's a strong motivation teaching that also to computer science students. And if I could dream, then I would like to teach a full module on that. And as you can see from that slide snippet on the left-hand side, I did that essentially 20 years ago. That's how long I'm invested in Isabelle, actually a little bit longer. Full module, full term, also 16 weeks, 2 or 3 hours lectures per week, weekly homework, teaching essentially computational logic, mathematical reasoning, and Isabelle in one combined course. Very similar to proposals that we've seen today, just using Isabelle instead of Lean. Isabelle also didn't look as nice as it does today, or Lean does today. There has been development over the last 20 years, definitely. Sadly, we're facing reality. We are currently working in an institution where computer science is being taught in a very applied way. I would even say it's more a software engineering program than a computer science program. And essentially, we only have one module in the first year that teaches discrete mathematics. And as much as Diego is doing a tremendous job in teaching induction proofs and first order logic to the students, there's only so much that you can do in one module, teaching mathematics to students that decided to go for computer science because they didn't want to do a math degree. At least large, certain number of our students made that decision based on the amount of math. So yeah, basic set theory, logic, and induction proofs and proof by contradiction and proof by case distinction are being taught. And then essentially we are missing the formal verification module. We are missing a lot of theoretical computer science modules that we see elsewhere. There's one module in the second year that is mandatory for the students called computer languages and representation, where there's usually half of the module spent on teaching them Haskell, which is the functional programming language. And that's essentially then the knowledge that we can build on. We are currently mainly offering Isabelle-based projects. So essentially, we are teaching Isabelle to students that want to do their third-year individual project, how it's called in the UK, with Isabelle, or in other countries, that is essentially what many people would call the bachelor's project or bachelor's thesis. We also do a little bit of formal methods teaching, more model checking based in the security module in the second term, but that is not what I want to talk about that. We just published a paper about that if you're interested in how to tweak at least some formal content into a module that otherwise teaches security. Feel free to have a look for that. And we have to say we also benefit on our conclusions that we draw, the success that we have also benefits quite a lot from Gihan here in the room, who is teaching Lean to the math and computer science students, so the students that take a combined degree, and some of those students doing a combined degree are also doing a final year project with us. And then essentially, it's more a transition from Lean to Isabelle than starting Isabelle from scratch. What is Isabelle? If you go to the Isabelle website, it's still essentially the description from the 80s when the system has been built for the very first time, highlighting it is a generic proof assistant. Proof assistant more in the sense of it's checking what we want to prove, and it's checking our proof steps. It's not really focusing on the degree of automation is pretty high these days, as it is for Lean as well, nor does it say a lot about all the other features that Isabelle has. In particular, and I don't know how that is for Lean, COG has a similar, has at least similar support. Besides the mathematics that is being formalized, the core reasoning engine that is implemented, there are also system technologies involved, like document generation, that you can generate PDF documents from your formal content, code generators that translates part of your formalization into programming languages, and there are code generators for various languages, including Haskell that our students know, and project management and dependency management that you can run projects and essentially do unit tests, and all those kind of things are provided as well. And as we've heard today a couple of times, a lot of the benefits from using such a tool and the comfort of using such a tool depends on what formalizations do you have available to you, which lemmas have already been proven, in addition to all the core mathematics that is being provided in the Isabelle distribution as such. The Isabelle community is pretty proud of something called the Archive of Formal Proof, or AFP for short, which I would informally describe for those of you that have implemented something in Python, for example, as PyPy for Isabelle, a large repository with formalizations that you can download and reuse or build your own formalization on. Don't want to go here everything through, but you can see there are different computer science topics, and the numbers here give you an idea about the number of entries that are available. There are a lot of more computer science topics like programming languages that are being formalized, security topics, but there's also quite a number of mathematics available here, both more traditional as more recent development in mathematics. And if we look at the statistics, the number of lines, oops, I don't have internet, the growth, kind of a proxy for the popularity, is pretty constant. The system is widely used, and we have individual AFP entries with nearly 10 million lines of code. So they can also be pretty large, or proof aspects, proofs, lines of proofs, if you want to count them that way. So a pretty successful system. In friendly competition with Lean, I think that is something good, because the advancements in both systems are being then transferred and exchanged between two systems, and different ideas are being evaluated. So I think we benefit from that. And I also, oops, where did I put my Isabelle? So I wanted to show you Isabelle. What you can see here is the JEdit frontend from Isabelle. We also have a Visual Studio Code-based one, but at the moment, the JEdit-based one is more mature, so that's why I'm using this. And because we started with the natural numbers game in the morning, I thought I quickly show you we can do essentially the same things in Isabelle as well. We can define our add functions, for example, and then prove that it is commutative, associative, things like that. We have also a window, or part of the screen here in the lower part of the window, where Isabelle gives us direct feedback about the definitions that we write. So that is essentially comparable to what we've seen in the last presentation with Lean on the right-hand side of the screen. We structure the work that we are doing in different theories or files. You can see the files on the right-hand side here in my screen setup, which also gives us an indication how much of those theories have already been checked. Here, everything is white and has essentially been checked, except for that number theory demo, which has only been checked up to essentially where my pointer is at the moment. And we have, for example, also query functionality. So if we don't remember how a theorem is being named, we can search for it either by names, or by, we're looking for a theorem where a certain constant is being describes the property over a certain logical constant, or we can search by types, or we need something that goes from an integer to an integer, and we can use that for finding information. But if we start introducing that to our students, we essentially leverage that our students know Haskell, and we don't expect our students at the beginning to do proofs. And also, if I'm designing a project idea for such a bachelor thesis, I always try to come up with ideas where if students don't want to do proofs in Isabelle, we still can come up with a good bachelor's project by just formalizing aspects and writing down properties instead of proving those properties or lemmas, doing the computer science approach and testing them, which is not as good as a proof, but testing is something that our students essentially know how it works, and that still is then sufficient for a good project result in a computer science degree. So we can, for example, specify merge sort, and here, sadly not syntax highlighted, I have the Haskell implementation, assuming that I already defined some function that gives me the first half of a list. I called that front over here, and one that gives me the second half of the list, the rear of the list, and I have some function that, given two already sorted lists, does the merge, resulting in a sorted list again. Merge sort is a simple recursive function. And if I look at that Haskell implementation and then look at the bottom of my top window, the syntax highlighted Isabelle definition looks very much the same. It also looks very similar to what we see in Lean. Maybe the difference here is that I specified that merge sort for an arbitrary type, prime A, or when we are talking, we call that alpha. So we use the prime essentially to denote Greek letters. We are not using the nice UTF encoding here for historic reasons. And I have a type class annotated here. Merge sort needs to compare elements. So on that, whatever type the list contains that I want to sort, that type needs to have a linear order defined. Yeah, we can define merge sort, and as said, with a little bit of Haskell background, our students can do that very quickly. And now we would like to prove properties over merge sort. And before we do that, we do essentially what was shown in the previous talk as well. Isabelle has those code generators. I quickly do a kind of alias definition where I limit the type to integers. Makes my life a little bit easier, and for the following, I don't need to annotate types. If I use this constant, then everything will be fixed to integer lists, just to make my life a little bit easier. And Isabelle has a value statement in Lean that was called eval. And as long as I'm staying in the executable subset of higher order logic, I can directly execute my functions here as well. And I can, for example, see, go to the output window again, that if I sort the empty list, I get the empty list. If I sort the list that only contains the one, I get the one. And I can use, can do essentially the usual testing that our students would do if they would implement that function Haskell or Python, where they run interactive tests and convince themselves that it works. I do that for a number of tests, and then hopefully it works or not. And then I can also state a lemma. So I'm trying to convince them or motivate students. Okay, now let's think about what are the properties that we want to prove. And maybe the first simple lemma is that sorting the list 1, 0, -1 returns the list -1, 0, 1. And the equivalent to the value statement on a tactic level is eval. That's not a trustworthy tactic as other Isabelle tactics are, because that's essentially taking that whole term, converts it into a computer program, runs it, and converts the result of the program execution back. And that process could be buggy, but it works very efficiently. And if you prove a theorem like that or a lemma, that is being recorded internally that you essentially cheated. And you can look that up. There's a query command. And also transitively, if you have a lemma that depends on a lemma where you cheated or where you used sorry, that you have in lean as well, you can trace that. But it has the nice feature you don't need about thinking about unfolding definitions. If you just want to check for a crowd function with all the arguments being crowned, what is the evaluation state property over it? It works directly, essentially fully automatically. And by that, we can encourage our students to think about the properties that we want to prove without really calling it a proof. If I state a wrong property, Isabelle has built in something called quick check, a counterexample generator. And I configured Isabelle here in a way that as soon as I type a lemma, it tries essentially by the structure testing approach to invalidate that lemma. And if it finds a counterexample, it shows me the counterexample. That's also something where if you write an obviously unprovable lemma here, the system immediately supports our students and says, hey, that isn't working well. Think about it. And I have to say that sometimes that's surprisingly powerful. Sometimes it doesn't it's not finding the obvious counterexamples as usual, but it's a very useful tool in general. And then we can either, students don't want to prove, saying, okay, we generate code and we do some more traditional software engineering-based testing, or we start proving lemmas. And for example, this would be a lemma stating, hey, our merge sort over integers that we defined actually returns a sorted list, and we are using a predefined predicate sorted that has been defined already in the Isabelle libraries. So that's a property or a constant defined as part of the lin order class. And Isabelle also supports things like hoovering over definitions. So if I do a click on that thing, it jumps directly to the theory where this is being defined, and I can explore that in more detail. So we have all those nice UI features. And we have something called Sledgehammer, which is an extremely powerful tool trying to prove lemmas. It's not a proof tactic. It's essentially a tool that tries to find a proof and then, if successful, would give us a proof tactic that we can use for discharging that goal. Here, in this case, it will not find a proof. So I'm stopping that for time reasons. It will time out after a moment. And that's then the point. So usually our students get pretty far by stating lemmas and calling Sledgehammer up to the point when they need induction. That's, I think, an experience that we all made. Induction doesn't work well automatically. So we need to do an induction proof. Isabelle, that might look like here, proof, induction. And similar to systems that we also have seen today, if I write down the first line, Isabelle responds with the subgoals, so the base case that we need to prove, or the two base cases here for the list with one element, for the empty list, the actual induction step. And it also shows me a proof outline in the high-level language that Isabelle is using, ISA. And I can essentially click on that. It copies that over into my editor window. What I had before. It discharges the subgoals with sorry. Again, that's cheating like in lean. And if I have no clue how to prove that, I can now just say Sledgehammer, and that should return now with BiSim, hopefully, or some alternative, except that I fear that Zoom at the moment is taking most of my CPU resources. But we see, or we hopefully have seen, so there's BiSim, BiAuto, which is another tactic. And again, I can just click on that, or BiForce, which is a third tactic that solves that goal. And the runtime for by simp and by auto 0.7 seconds, by force only 0.5. So maybe I would like to say prove that by force. Anyway, it's a nice statement. And with that, we are very successful actually in turning our students into proof engineers. And they do pretty impressive stuff in their bachelor's projects. Of course, for proving merge sort correct, we also need to prove that we are not losing any elements. I skipped that due to time. And that's the demo. One thing that I want to quickly show with the demo. So you might have seen I had that Haskell statement in there. I have text here that also, for example, contains weird things like @const merge. That is being checked by Isabelle, that constant merge actually exists. And I can generate PDFs from that. So there, the Haskell code is being formatted a little bit nicely. And then I know that constants that are being referred to, or lemmas that are referred to, that are printed here, are being checked by Isabelle. And I can essentially hope that there are less typos in the formal aspects of the document. Everything is being generated by references to Isabelle definitions. There are guaranteed no typos because Isabelle has checked everything. And then just to give you an example, what were our students able to do? We had students formalizing and verifying properties over data structures, such as blockchains, always a hot topic with our students. Last year, we had a student doing program verification over C programs, looking at numerical overflows, so bounded integers, what security impacts that has, including finding an issue where a security patch wasn't actually patching the problem in a real-world program, so really nice success. We formalized polyglot programs, so two programming languages, same program is valid in both. We came up with properties that those programs need to satisfy that they actually compile in both languages. Teddy, that is here in the room, has done a project on homomorphic encryption. Amy, that is here, has done a project on formalizing machine learning, access control systems. Last year, 2 years ago, also supervised the project where we implemented algorithms for symbolic computations of derivatives and verified them so that you don't need to guess the derivative. And that then is also what we're essentially doing in our research. So Diego is leading a project on defining formally the semantics of the programming language Solidity, which is used for smart contracts. Formal semantics means we can guarantee that it is consistent. We have a clear meaning what every operation that programming language provides has. And the goal is to developing a verification environment. And in this work, also Billy, one of our PhD students, is involved. He's, I think, not here today. And Asad is working on that as well. And yeah, we are doing formal verification of neural networks for showing safety properties. That's mainly the work that Amy is doing. And as part of that, we are also formalizing parts of mathematics if needed. For example, interval arithmetic. It's also something that Amy and Teddy here in the room and I did together. And we can confirm experience that other people mentioned this morning already. That was a project that we thought of, okay, that's 3 or 4 pages in the math book. It will take us a couple of weeks, maybe a few months. I think it took us essentially a year. There were quite some, we didn't find a proper mistake in that math book, but for example, they were very relaxed in jumping between intervals and sets and multi-sets. When you do it formally, you have to be very precise when what is being required, and proofs that were written down in a line, as you obviously can see, took quite a while to really understand what the actual argument of that proof is. And then also to explain that to Isabelle, of course. Conclusion is, I think there's clearly a large overlap between mathematics and computer science. In particular, if we're talking about theorem provers, we are not only implementing them, we are also formalizing mathematics. We are using formalized mathematics. So I think clearly we should work together in those areas. And if we want to teach such systems to students that are more approaching the problem from a computer science background with little proof and logics or math background, then trying to introduce them to a system as this is a type of programming environment where we can evaluate definitions, play around with them, essentially write tests for the properties that we otherwise would prove, and then slowly start introducing them to the proving. And reasoning actually works pretty well. I'm not saying that this approach works with in a module with 200 students that every computer science student has to take. Clearly, that is an approach that works well for us with a couple of students that are really interested in that topic and are approaching us because they want to learn how to use Isabelle or similar systems.
So thank you very much, Achim, and yeah, really interesting compliment. So again, just an opportunity to invite questions, any comments and discussion around what we've heard from Jeremy and from Achim. Patrick.
I've got a quick comment about Jeremy's talk. It's not really a comment for Jeremy, it's for a comment for people who may not know a lot about all this. So Jeremy mentioned that we need a powerful automation in this story, but this is really tricky. I mean, as Heather explained in her talk, sometimes we want the not too powerful automation. So she explained that she did also dumbed down versions of some tactics. And the thing is that as teachers, we want the computer to do automatically stuff that we would not ask questions about on paper. I mean, we don't want students to provide justification to the computer that we do not want to see on paper, but this is a very vague specification. It's not even consistent because we change our mind about what should be explained. And by the way, this is also part of the reason why my teaching library is so customizable, because each teacher can have a different opinion and change their mind. And we saw this morning in the first talk by Atina that some students use CC to do a natural number game level about logic, and that CC tactic was just crushing the exercise completely. So it's clear that this was not the intended. So Atina emphasized the use of repeat, but it was repeat CC. So it was repeat, just do the exercise for me. So that's one point. And also a quick comment about the teaching resources, something that we need to keep in mind when we see all those talks about successful experiments of people using a new technology to teach, is that as with any pedagogical experiment, what you see is there are teachers who are extremely enthusiastic about some new way of teaching, and it's successful partly because they put insane amount of hours of work. And so I put completely insane amount of work in my teaching library, and I know that Heather did that too. And so we really need to find ways to reuse more of this effort. So I encourage everybody here to try to use existing material and tell us if it's not good enough for their use, so that we can scale up, and that not everybody using ProfAssistant for teaching needs to do like Heather is doing, 20 minutes interviews with every student twice a semester, and just does not scale. That were my comments.
Absolutely. No, thank you, Patrick. And in fact, one of the things that today has emphasised to me is how many excellent resources there are out there that probably we need to all be looking at before we decide to implement and design our own resources. As you say, that would be very valuable, not just in terms of evaluation, but in terms of efficiency. I'm also reminded that in education research, almost inevitably the conclusions are that this works sometimes in some situations for some of our students, and and that's the challenge of any sort of education research and interventions that we do, and also that you do something different, and as you say, with enthusiasm, and inevitably that has a positive effect on the students. It's well known. So Achim.
I completely agree. We need to be very careful, firstly, distinguish between the use of theory improvers in research and teaching, and also what features we want our students to use in teaching. In Isabelle, we also have the opportunity or possibility to strip the system down or you use self-defined theory. So if you look carefully at my numbers formalization, I did introduce my own definition of natural numbers, because with the standard one, the automatism of Isabelle would kill all those proofs automatically. And that would be pointless when I use that simple example for teaching induction to students. And the temptation to just say by simp auto would be too large, and I completely can understand that. So I need to strip that system down that students really are forced to use the proof methods or lemmas that I want them to teach at that moment. So there's this, yeah, fully agree with what you said.
Yeah, if I could respond also. I mean, I also fully agree with everything that that Patrick has said. I mean, with automation, I am hopeful that we can at least do better. We can get better at, you know, having specific customizable automation. So, you know, at any point in a course, we should be able to specify what students are allowed to do and have the automation permit that. I think for a while, we'll still have the situation where, you know, you'll always have two choices. You know, you can either err on the side of caution, you know, you kind of restrict your automation just to make sure it's not getting too much. Or, you know, you say, look, I really want to make sure that it does all the obvious steps, possibly at the expense of doing too much. So I think there, you know, so it is a fine line to walk. Yeah, I personally would sort of err on the side of having automation that does too much, with the expectation that you also want students to write pen and paper proofs that are graded. You want, you know, you want graders looking over them saying, no, that's. So I think, you know, the question is where the correction comes in and so on. And as far as reusing materials, I mean, it's similar to the situation with textbooks. There are a lot of textbooks out there. And one reason that there are so many textbooks is that, you know, everybody teaches a course and doesn't, you know, doesn't quite like any textbook and then kind of writes another one. But I think with Lean, we now have the opportunity to kind of reuse parts and mix. So in other words, if there are libraries of platforms and materials, that gives, I mean, so for example, anybody can design a course based on Patrick's, you know, verbose Lean, and then maybe customize or add or restrict and change. And so I think that's an interesting new possibility.
I mean, also there's, the more automation do you have, the more quicker students can prove interesting stuff, which can be motivating. And then essentially there's the idea of teaching it top down or bottom up. When I started in the old Isabelle course from 20 years ago, essentially we started with only substitution and rule application and the basic logical rules, and no simplifier, no automatic tactics. It teaches you very well how to prove in a logical framework, but each simple proof is already a hell of work, which can be frustrating depending what the backgrounds of your students is. So yeah, you need to find the right way that fits the student cohort and the environment that you're teaching in. There's not one solution that works for everybody.
Sure. Yeah, absolutely. And that challenge anyway in teaching mathematics and throughput in mathematics, that often we're teaching students things they already think they know. Why do I need to listen to this? Why do I need to go through and write this proof out? We already know this. I've known this since I was 5, 6, 7 years old. Absolutely. Any other comments, questions?
So you talked about serious formalization of the protocols, and this is all happening in Isabelle. And when I started formalizing mathematics, I realized that the mathematics I was interested in, it was going to be really hard to do in Isabelle because I was using dependent types. And I was just wondering, do you run into that?
Oh, that's an interesting and hotly debated
question. People,
Yeah, I think we can all hear it online as well.
The question was about dependent types.
You need them in program verification.
No. Larry Paulson, one of the authors of Isabelle, would also claim you don't need them of modern mathematics.
Yeah, but he's wrong about that.
I would say there are different opinions, and we have something called locales in Isabelle, which is, at least to the current understanding, the closest that you can get to dependent types before the combination of higher order logic with those extensions becomes most likely inconsistent. And Larry at least would claim that every challenge he got, he could formalize nicely in Isabelle with locales. I think that I would say not wrong. That's an open problem that we still need to see. And on the downside with dependent types, automation is much harder.
Oh, absolutely.
Yeah, so
You
that's
don't
the
feel like you're missing them. That was my question. You don't kind of think, oh, this would be so much easier with dependent type. When doing program verification.
No, sometimes we are thinking dependent types would be nice, but not in the sense of it would be so much more nicer.
Interesting, thanks.
Okay, thank you. Any further questions, comments?
I had one comment,
Yeah.
sorry, that I meant to say before this question, talking about restricting when big tactics and stopping students from using them, just to comment that this Lean 4 game framework has that implemented. You can you can have tactics there, but students can't use them until they've unlocked them. That was the way we got around that with in the natural number game, because there are, obviously there are tactics that can solve every level of the natural number.
Absolutely. Okay, last opportunity. Okay, well, thank you ever so much. Can we just give a round of applause to all our speakers today, please? Thank you. And I'm abundantly aware that whilst Gihan has asked me to host today, really this wouldn't have happened without Gihan and his sort of network of friendships and professional contacts and all this sort of stuff and all the work he's put in behind the scenes. So can we thank Gihan as well? Now, I know some people will want to disappear in a moment. We do have an evaluation form. Gihan, I've sent you a link to it actually on Teams and in Outlook. So if you can drop that in the Zoom chat, that would be great. We'll also email it round. 3 very simple questions, and then if you do have a little more time, a few more detailed questions. I know that some people will disappear now. If you do want to stay around online or in the room, there's going to be another workshop that Gihan is going to give now based on mathematics in Lean that Jeremy, Patrick, and various others have put together. And that will introduce us to some sense more advanced mathematics than we've seen so far in the natural number game. Okay, so we'll leave it there. We'll break for let's say 10 minutes before we come back for that. So 10 minutes, and then we'll come back for Gihan's workshop.